An invisible rain of atomic shards constantly bombards our planet. These are cosmic rays, high-energy messengers carrying secrets from across the cosmos. By the end of this journey, you will understand how to interpret their hidden language, revealing stories of black holes and stellar explosions. What celestial engines can hurl a single particle with the force of a baseball? And what do these signals whisper about the dark matter that binds the universe? How does it feel to know the void is not silent, but speaking to us? Victor Hess's daring balloon ascent in 1912 did more than just measure the air. It tore a hole in our understanding of reality. High above the Earth, with his electroscopes clicking away, he found something astonishing. The radiation did not fade away as he rose from the ground. It grew stronger. This simple, brave experiment proved for the first time that an invisible rain was pouring down on us from the depths of space itself. He called them cosmic rays, but for years their true identity remained a tantalizing secret. Scientists initially believed they were a form of pure energy, like gamma rays. But the particles defied easy explanation. They were too powerful, too penetrating. The real breakthrough came when we realized these were not rays of light at all. They were matter, bullets. The cosmic rays bombarding our planet are primarily the shattered pieces of atoms, protons, and atomic nuclei, hurled across the galaxy at speeds almost too fast to comprehend. Think of a single proton, a speck so small it is almost nothing, accelerated to energies that rival a professionally thrown baseball. This is not a gentle rain. It is a hurricane of atomic shards. Our quest to understand them has driven us to build ever more sensitive ears to listen. From the humble balloon to colossal observatories like the Pierre Auger array in Argentina, which spans an area larger than a major city, we have chased these messengers. This historical journey reveals a vital truth. The universe is not a quiet, static painting. It is a violent, dynamic arena, and these particles are its direct emissaries. To truly grasp the messages they carry, we must first ask a more basic question. What exactly are these cosmic bullets made of? So what exactly is this invisible hurricane made of? It is not a single substance but a whole family of atomic shrapnel, each piece with its own story. The vast majority, about 90%, are simple protons, the bare nuclei of hydrogen atoms. Another 9% are helium nuclei, and the remaining 1% is where things get truly fascinating. This tiny fraction contains the shredded remains of every element we know, from carbon and oxygen all the way up to iron and uranium. This is not a random assortment of space dust. It is a specific chemical fingerprint, a cosmic inventory that points directly to its origin. These particles are not born in peaceful places. They are forged in the most violent events the universe can produce. A supernova explosion, the death scream of a massive star, creates immense shock waves that ripple through space. These waves act as natural particle accelerators, far more powerful than anything we can build on Earth. They grab hold of atomic nuclei and fling them across the galaxy at velocities so close to light speed that their energy becomes almost unimaginable. Other potential sources are even more extreme. Active galactic nuclei, where a supermassive black hole violently consumes stars and gas, can fire jets of matter across millions of light years. Gamma-ray bursts, the brightest explosion since the birth of the cosmos, might also contribute to this relentless particle storm. Each atomic nucleus that strikes our atmosphere is a unique syllable in a cosmic message. A fragment of iron tells a different story than a lone proton, whispering clues about the specific type of cataclysm that created it. But this message faces a perilous journey. How does a single particle fired from a dying star millions of years ago manage to find its way to our tiny world? But this message faces a perilous journey across a sea of invisible forces. A single cosmic ray proton fired from a supernova remnant does not travel in a clean, straight line. Its voyage is an epic million-year odyssey through the galaxy's turbulent magnetic landscape. Because the particle carries an electric charge, it is pushed and pulled by these magnetic fields, forced into a spiraling, chaotic path. It is a pinball in a cosmic machine, ricocheting endlessly. This relentless scattering has a profound consequence for us. It randomizes the particle's direction of arrival at Earth. By the time it reaches us, we cannot simply look back along its path to find its home. Trying to pinpoint the origin of a specific cosmic ray is like trying to find which tree a single leaf came from after it has been tossed and turned in a hurricane. The journey itself leaves marks. As these high-energy particles race through the thin soup of gas and dust between the stars, the interstellar medium, they sometimes suffer direct collisions. A heavy nucleus like iron can slam into a stationary atom of interstellar hydrogen. The impact is so violent it shatters the traveler, a process called spallation, fragmenting it into lighter, secondary elements. This means the very composition of the cosmic rays that finally reach us is a changed record, a story not just of their birth but of their long and violent voyage. Every particle that strikes our atmosphere carries this encrypted travel log. To read the original message, we must first learn to decode the scratches and scars from the journey itself. This is why our detection methods on the ground must be so sophisticated, designed to listen not just to the shout, but to the subtle echoes of an unimaginable trip. This vast particle shower, an invisible rain of secondary messengers, is our only direct link to the original cosmic bullet. The primary ray itself, the single proton or iron nucleus from a distant galaxy, never touches the ground. It meets its end high in the upper atmosphere, in a spectacular sacrifice that creates a fleeting, downward expanding firework of energy. This event, known as an extensive air shower, can contain billions of secondary particles spreading over an area the size of a small town by the time it reaches the Earth's surface. Our ground-based observatories are designed to catch this expanding wave. At the Pierre Auger Observatory, thousands of individual detector tanks are spread across the Argentine pampas. Each tank is filled with pure water. When a particle from the shower zips through this water faster than light can travel in that medium, it produces a faint, ethereal blue glow called Cherenkov radiation. It is like the sonic boom of a jet but made of light. By precisely timing when this wave of particles hits different tanks across the vast array, scientists can triangulate the shower's core and trace its path backwards. This allows them to reconstruct the original particle's trajectory and, even more importantly, its staggering energy. The density of the shower tells them the mass of the primary cosmic ray. Was it a lightweight proton or a heavyweight iron nucleus? This entire intricate process, listening to the echoes of a collision that happened miles overhead, is how we begin to translate the message. But to hear the full story without the atmosphere's distortion, we must also listen from above. High above the Earth's protective veil, a silent laboratory drifts through the void. The Alpha Magnetic Spectrometer, mounted on the International Space Station, listens to the cosmos without any atmospheric interference. This instrument catches the primary cosmic rays directly, before they ever have a chance to shatter and create their cascading showers. It is like having a microphone right at the concert instead of listening from the parking lot. The heart of this detector is a powerful magnet. when a charged particle, like a proton or an iron nucleus, flies through this magnetic field, its path bends. The amount of this bend tells scientists everything about the particle. A heavier particle or one with more momentum will resist the turn, while a lighter one will curve more easily. By measuring this curvature with extreme precision, the spectrometer can identify the particle's charge and its mass, essentially reading its identity card. Inside the detector, a component called a calorimeter acts as a final stop. It captures the particles entirely, measuring the total energy they release upon impact. This direct sampling provides a pristine, unaltered record of the cosmic ray's original properties. The data is incredibly clean, free from the atmospheric noise that ground arrays must carefully filter out. This allows scientists to build a precise inventory of what is actually arriving from deep space. The combination of these two methods, the ground-based ears listening to the echoes and the space-based eyes seeing the original messengers, creates a powerful partnership. By comparing the data from both, researchers can cross-check their findings and resolve discrepancies. This dual approach gives us a much more complete and reliable picture of the cosmic ray spectrum, from the lowest to the highest energies. It is through this pristine space-based data that we begin to see the true anomalies, the subtle fingerprints in the cosmic message that do not fit our expectations, pointing toward mysteries we are only beginning to formulate. When we chart the number of cosmic rays arriving at different energy levels, we find a story written in sharp, unexpected turns. The graph does not form a gentle slope. Instead, it is punctuated by two dramatic bends, features that scientists have named the knee and the ankle. These are not smooth transitions. They are sharp breaks in the narrative, and they hold the keys to understanding where these particles come from and how they travel. The first of these, the knee, occurs at an almost unimaginable energy level of 10 to the 15 electron volts. At this point, the number of particles we detect begins to plummet far more steeply. It is as if a cosmic dam has been reached. The leading theory suggests this knee marks the absolute upper limit for our own galaxy's natural particle accelerators. Supernova remnants, the powerful shockwaves from exploding stars, can only fling particles so fast. Beyond this energy threshold, the particles become too powerful to be contained by the Milky Way's magnetic fields. They simply escape, leaking out into the vast intergalactic void. This is why the flux drops so sharply. The most energetic galactic messengers are abandoning their home. But the story does not end there. As we push to even higher energies, past a staggering 10 to the 18 electron volts, the plot twists again. Here we find the ankle, a point where the cosmic ray spectrum mysteriously flattens out and begins to rise once more. This is the signature of a new cast of characters entering the stage. The particles we detect at these ultra-high energies are no longer from our own galaxy. They are extragalactic travelers, born in cataclysms of a scale that dwarfs our local supernova. Their likely sources are the most violent engines in the cosmos, active galactic nuclei, where supermassive black holes shred entire stars and power jets of matter that cross millions of light years. These two features, the knee and the ankle, are the fundamental grammar of the cosmic ray language. They are the chapter breaks in a grand cosmic story, separating the local tales from the epic sagas that arrive from beyond our galactic shores. Deciphering the precise physics behind these spectral bends remains one of the great quests in modern physics, and it is this search that directs our gaze toward the most extreme and baffling particles of all. One single particle carries the kinetic energy of a professional fastball. This is the staggering reality of an ultra-high-energy cosmic ray, a subatomic bullet with a nucleus smaller than an atom yet packing a punch exceeding 10 to the 18 electron volts. Their existence alone challenges the very limits of known physics, forcing us to ask what kind of cosmic engine could possibly achieve this. Imagine the most powerful particle accelerator we have on Earth, the Large Hadron Collider. Now picture a natural process in the distant universe that makes our mightiest machine seem feeble by comparison. The prime suspects are the most violent events we can conceive in distant galaxies. Monster black holes at the centers of active galaxies can whip up immense magnetic fields, firing focused jets of plasma across cosmic distances. The chaotic collisions of neutron stars, events that shake the very fabric of spacetime, might also serve as natural cannons for these particles. Yet there is another, more fundamental puzzle baked into their journey. The universe is not empty. It is filled with the faint, cold echo of the Big Bang itself, the cosmic microwave background radiation. This omnipresent glow acts like a cosmic fog for these ultra-fast travelers. A proton with such immense energy should inevitably collide with this background light, a crash that would drain its energy and ultimately stop it from traveling more than a few 100 million light-years. This theoretical barrier is known as the GZK Cutoff, but here is the enigma. Our detectors have recorded particles that appear to have sailed right through this wall. They arrive with energies that, according to our best models, they should have lost long before reaching us. This means one of two incredible things. Either these particles come from relatively nearby sources within our local cosmic neighborhood, defying our ideas about what can produce such power, or our understanding of physics itself is incomplete at these extreme energies. Every one of these ultra-high-energy cosmic rays is therefore a double mystery. It is a message about an unimaginably violent event and a challenge to the fundamental laws that govern its journey. To solve this, we must become cosmic detectives on the grandest scale, using the universe itself as our laboratory. Finding the source of a cosmic ray is like trying to find the origin of a whisper in a hurricane. The magnetic fields of the galaxy scramble their path so completely that tracing a single particle back to its home is impossible through direct sight. We must become cosmic detectives, solving the mystery through indirect clues and secondary evidence. The breakthrough comes from the aftermath of their journey. When these high-energy particles interact with the dense clouds of interstellar gas near their birthplace, they do not just pass through quietly. They create a cascade of other particles, including two unique messengers that travel in perfect, straight lines, gamma rays and neutrinos. Unlike the bent and scattered cosmic rays, these signals fly true, pointing like unwavering arrows back to their point of origin. This is the heart of indirect cosmic ray astronomy. We are not looking for the bullets themselves, but for the muzzle flash. Our most powerful tool for this hunt is gamma-ray light. Space telescopes like the Fermi Gamma-Ray Space Telescope scan the entire sky, mapping the universe in these high-energy photons. They look for bright, persistent hotspots of gamma radiation. One of the most famous of these is a supernova remnant known as RxJ 1713.73946. The intense gamma rays pouring from this expanding shell of stellar debris provide compelling evidence that the shock waves from that ancient explosion are actively accelerating particles to near light speed, a cosmic ray factory in action. The next generation of observatories, like the upcoming Cherenkov Telescope Array, will take this search to a new level of precision. By correlating this gamma-ray map with the data we have on cosmic ray composition from instruments like the Alpha Magnetic Spectrometer, a powerful picture emerges. When we see a gamma-ray hotspot that also corresponds with a specific mix of heavy atomic nuclei detected in the cosmic rays, the case becomes strong. We can begin to confidently say that specific supernova remnant or that distant active galaxy is a proven source. This multi-messenger approach, combining the clues from charged particles, gamma rays, and neutrinos, is the only way to translate the full scrambled message. It is a symphony of different signals, each playing a different part of the same cosmic story. Our own star provides a constant, nearby example of this cosmic particle acceleration. While the Sun cannot match the raw power of a distant supernova, it offers a front-row seat to the fundamental processes at work. During periods of intense magnetic activity, the Sun unleashes colossal eruptions known as solar flares and coronal mass ejections. These events act as powerful local accelerators, hurling billions of tons of solar plasma and charged particles out into space. We call these solar cosmic rays or solar energetic particles, and they create a tangible, sometimes dangerous connection between the cosmos and our daily lives. A direct hit from a major solar storm is not just a light show. These high-energy particles can fry the delicate electronics in our satellites, silencing communication and GPS networks. They pose a severe radiation risk to astronauts in orbit, who lack the full protection of Earth's atmosphere and magnetic field. And when these particles slam into our planet's magnetic shield, they can induce powerful electrical currents in the ground itself. These geomagnetically induced currents have the potential to overload transformers and cause widespread, long-lasting power outages, turning the lights off for entire cities. This is the reality of space weather, a forecast written in the language of solar cosmic rays. But this hazard is also an unprecedented opportunity. By studying these particles, we have a natural laboratory right in our celestial backyard. We can observe the entire process of acceleration, from the initial magnetic explosion on the Sun's surface to the particles' arrival at Earth, all in a matter of hours or days. This allows us to test our theories about how shock waves and magnetic fields energize matter on a manageable scale. The composition of these solar particles is a direct sample of the material from the Sun's outer atmosphere, its corona. By analyzing them, we learn what the Sun is made of and the precise conditions that lead to these violent eruptions. Mastering this local dialect of the cosmic ray language does more than just protect our technology. It gives us a universal key. The same basic physics that creates a solar flare on our Sun likely governs the eruptions on countless other stars across the galaxy. Every solar storm we decode helps us understand the wider, more violent stellar universe, linking the familiar glow in our sky to the distant engines lighting up the cosmos. One of the most thrilling chapters in the cosmic ray story is written in the language of antimatter. We are not just detecting the ordinary shrapnel of atoms, but also their ghostly mirror images. Sophisticated experiments like the Alpha Magnetic Spectrometer and the PAMEL satellite have been meticulously counting these rare arrivals, identifying positrons, which are the antimatter twins of electrons, and even antiprotons. Their very existence in cosmic rays is a profound puzzle. Many are created as secondary products, the inevitable fallout when a primary cosmic ray, like a proton, smashes into a stray atom of interstellar gas. This collision is so violent it can literally conjure matter and antimatter from pure energy, a process predicted by Einstein's famous equation, but the data holds a tantalizing anomaly. At high energies, there are more positrons arriving than our standard models of cosmic ray collisions can explain. It is an unexpected surplus, a mysterious excess that has set the world of physics alight with possibility. Could this be the long-sought signature of dark matter? Some theories suggest that when two hypothetical dark matter particles collide and annihilate, they could produce a shower of standard particles, including this very excess of positrons we are detecting. It is a ghostly fingerprint from the invisible majority of the universe, yet there are other, equally compelling explanations. The spinning corpses of dead stars, known as pulsars, act as powerful natural dynamos. Their intense magnetic fields can whip particles to incredible speeds, potentially creating positrons in abundance. A few nearby pulsars could be flooding our local galactic neighborhood with these antimatter particles, creating the apparent surplus. Each antiparticle we detect is like a rare and exotic word in the cosmic vocabulary, a syllable that could be spelling out the name of dark matter or the signature of a stellar corpse. The careful, painstaking measurement of this antimatter component is more than just a census. It is a critical stress test for our entire understanding of how cosmic rays travel and interact, and even for the fundamental laws of particle physics. This mystery of antimatter messengers leads us directly to the greatest and most baffling puzzle in all of cosmology. The very particles we have been listening to could be carrying a whisper from the dark side of the universe. Dark matter, the invisible scaffolding that holds galaxies together, has evaded every direct attempt at detection. Yet, it might be revealing itself through subtle fingerprints in the cosmic ray flux. Many physicists believe this mysterious substance is made of hypothetical particles known as weakly interacting massive particles, or WIMP. If this is true, then wherever dark matter is densely concentrated, these WIMP could occasionally collide and annihilate each other. When they do, they would transform into a burst of familiar particles we already know how to detect, including protons, antiprotons, positrons, and gamma rays. This is the grand hope. Our cosmic ray observatories are not just studying stellar explosions. They have become the most sensitive dark matter hunters in existence, sifting through countless detections for a single, anomalous signal. Scientists are not looking for a random spike in the data. They are searching for very specific spectral features, a precise bump or a cut-off in the energy spectrum of these secondary particles. They are hunting for an overabundance of positrons or antiprotons at certain energies that simply cannot be explained by any known astrophysical process, like a pulsar or a supernova. It would be a signature that screams of something entirely new. So far, no such definitive signal has emerged. The tantalizing excess of positrons seen by instruments like the alpha magnetic spectrometer could still be explained by nearby pulsars. The hunt is a meticulous process of elimination, ruling out every conceivable astrophysical source until only the truly exotic remains. This search connects the colossal scale of the cosmos to the quantum realm of particle physics. Every time a detector on Earth or in space registers a particle, it is listening for an echo from the dark universe. The potential to finally decode a message from this hidden majority, to understand what 85% of the universe is actually made of, adds an almost unimaginable weight to this quiet, persistent research. We are not just translating the stories of stars. We are trying to read a language written by the invisible hand that shapes reality itself. Our galaxy is not a silent void but a humming library, its shelves defined by invisible lines of magnetic force. This is the Milky Way's magnetic field, a structure so vast and diffuse it is almost nothing, yet it holds a profound power over the cosmic messengers we seek to understand. By earthly standards, this field is incredibly weak, millions of times fainter than a common refrigerator magnet. But across the immense, light-year-spanning distances of our galaxy, its influence is total. It acts as a cosmic librarian, a meticulous but chaotic archivist that carefully files and often scrambles the incoming messages from deep space. The field itself is not a simple, neat structure. It possesses a dual nature. There is a regular, large-scale component, a slow and steady current that flows along the spiral arms of the galaxy. Woven through this order is a turbulent, small-scale component, a frothing sea of magnetic knots and whirlpools that twist and scatter the paths of any charged particle daring to pass through. A single cosmic ray proton does not travel in a straight line. It is forced into a spiraling, chaotic dance, ricocheting for millions of years before it finally arrives at our doorstep. This is the fundamental reason we cannot simply look up and trace a particle back to its source. The original direction has been completely randomized by this magnetic maze. To have any hope of backtracking a cosmic ray to its origin, we must first learn the precise layout of this labyrinth. We need a detailed map of the galactic magnetic field. How do you chart something you cannot see? Scientists have developed ingenious techniques to illuminate this invisible scaffold. One method involves observing the polarization of starlight. As starlight travels through the galaxy, dust grains aligned by the magnetic field polarize the light, subtly twisting it. By measuring this twist across the sky, we can infer the field's orientation. Another powerful tool comes from synchrotron radiation. When high-energy electrons spiral around these magnetic field lines, they emit a distinctive radio glow. Mapping this synchrotron emission across the Milky Way gives us a direct picture of where the magnetic fields are strongest and how they are structured. The consequence of all this magnetic filtering is that the cosmic ray data we collect is not a pristine, direct signal. It is a heavily processed record, a message that has been copied, edited, and shuffled by the galaxy's great magnetic lens. Every particle's energy, its type, and its apparent direction of arrival have been shaped by this long journey. To accurately translate the original message, we must first learn the complete grammar of this magnetic field. We must understand its strength, its turbulence, and its large-scale shape so we can run the cosmic film in reverse. This is not a simple calculation. It requires some of the most powerful supercomputers in the world, running complex simulations that model the paths of billions of particles through a simulated galactic magnetic field. Only by mastering this digital model of our cosmic library can we hope to find the true shelves where these incredible stories began. This digital decoding process is a symphony of pure computation, a conversation between raw data and raw processing power. Think of the data collected by an observatory like Pierre Auger, a sprawling network of detectors recording the echoes of a cosmic event. This is not a simple, clean signal. It is a chaotic spray of information, a complex pattern of timing and energy deposited across thousands of individual sensors. To reconstruct the original particle from this scattered aftermath is like trying to deduce the exact shape, size, and force of a stone by only listening to the splashes it makes in a vast, dark pond. This is where the supercomputers come in. These are not ordinary machines. They are dedicated cosmic engines running simulations of staggering complexity. They use a method known as Monte Carlo simulation, a technique that relies on generating millions of random possibilities to model a chaotic system. The computer essentially asks over and over again, what would happen if a proton of a certain energy struck the atmosphere at a specific angle? It then simulates the entire cascade, the billions of secondary particles raining down, and predicts exactly what the detector array on the ground should see. This digital shower is then compared pixel by pixel to the actual data from the real event, but the journey does not end there. The simulation must also account for the Great Scrambler, the galaxy's magnetic field. The computer models this invisible maze, tracing the probable path of the particle backwards through millions of years of magnetic turbulence. Scientists can pose a limitless series of what-if questions to the machine. What if the source was a nearby supernova remnant instead of a distant active galaxy? What if the magnetic field in this spiral arm is 10% weaker than we assumed? Each variation creates a new simulated outcome, which is then matched against the mountain of real observations. The models that produce the best fit, that most accurately predict what our detectors actually record, rise to the top. This is how we crack the code, not with a single brilliant insight, but with the relentless brute force of computation, testing every conceivable key until one finally turns the lock. This synergy reveals a universe that is not a collection of isolated events, but a deeply interconnected web. The path of a single particle from a dying star is woven into the magnetic fabric of the entire galaxy, and we are now learning to read that magnificent tapestry. The same particles that carry tales of galactic violence may have been the quiet midwives to life on our own planet. This is a profound and speculative connection, linking the cosmic to the biological in a way that reshapes our origin story. We often think of intense radiation as purely destructive, a force that damages cells and unravels DNA. Yet, in the primordial soup of early Earth, a moderate flux of cosmic rays could have provided a crucial spark. Their energy, deposited steadily over billions of years, might have been a hidden driver of probiotic chemistry. Imagine a cosmic ray piercing the ancient atmosphere. As it collides with molecules, it leaves behind a trail of ionization, a wake of electrically charged particles. This ionization could have acted as a catalyst, encouraging simple atoms to link into the complex organic molecules essential for life. Some researchers even propose that these charged trails influenced the formation of thunderstorms, perhaps guiding the lightning strikes that experiments show can create amino acids, the very building blocks of proteins. Beyond that initial spark, the constant drizzle of cosmic radiation would have provided a low-level source of genetic mutation. While too much radiation is lethal, a gentle, persistent background can introduce just enough variation into early life forms to accelerate evolutionary change. It becomes a universal mechanism for shuffling the deck, pushing simple organisms toward greater complexity at a faster pace than a perfectly sheltered world would allow. This idea remains controversial, a hypothesis dancing on the edge of what science can ever truly prove. Yet it offers a breathtaking vision. The same iron nucleus that once flew from a supernova, carrying a message about stellar death, might have indirectly guided the chemical processes that led, eons later, to you listening to this story. The universe does not feel so distant when you consider that its most energetic messengers may have written themselves into our very blueprint. This entire cosmic conversation operates on a grand galactic loop, a continuous cycle of creation, journey, and transformation. To truly understand the message, we must follow a single particle through its epic life story. It all begins with a violent birth inside a cosmic engine. A supernova's immense shockwave, or the relativistic jet from a feeding black hole, acts as a natural slingshot. This engine grabs a simple atomic nucleus, a proton or a fragment of iron, and flings it into the void with almost incomprehensible force. This is the moment of acceleration. The particles launch into its million-year odyssey. Once free from its source, the particle embarks on the long voyage through the galaxy. But this is not a straight shot. It is a spiraling, chaotic pinball game through the Milky Way's invisible magnetic maze. The particle is pushed and pulled, its path randomized so completely that its origin becomes a blurred memory. This journey is not a safe passage. The space between stars is not entirely empty. It is filled with a thin mist of atomic gas and dust. During its travels, our cosmic ray might suffer a direct collision with a stationary atom of interstellar hydrogen. The impact is catastrophic, shattering the traveler in a process called spallation, fragmenting a heavy iron nucleus into lighter, secondary pieces. Sometimes these collisions produce other messengers, like gamma rays or neutrinos, that fly away in a straight line, acting as a bright flare pointing back to the site of the interaction. After perhaps millions of years of this turbulent wandering, a tiny, fortunate fraction of these particles finds its path intersecting with our tiny world. It screams into the upper atmosphere, and in a final, brilliant sacrifice, it shatters, creating a sprawling firework of secondary particles that rain down over miles. This is the extensive air shower that our ground-based detectors are built to capture, the echo we listen to so carefully, but the cycle does not end at our detectors. Many particles are eventually lost, leaking out of the galaxy's magnetic grip into the vast intergalactic void. Others might have a different fate. A particle that has lost some energy during its long travel could be swept up by another passing shockwave from a different supernova, receiving a second boost, a re-acceleration that sends it on another lap around the cosmic circuit. This is not a one-way trip. It is a continuous recycling process, a fundamental rhythm of our galaxy where matter and energy are constantly being broken down and rebuilt. Every cosmic ray we detect is a single snapshot from this endless loop, a frozen moment in a story that spans the galaxy and connects stellar death to the very instruments we use to listen. If you could see the sky with cosmic ray eyes, it would not be a featureless, uniform glow. The universe would reveal itself in subtle contrasts of light and shadow, a hidden topography of particle fountains and cosmic voids. This uneven distribution has a name, anisotropy, and mapping it is one of the most difficult challenges in all of astrophysics. The galaxy's magnetic fields act like a powerful blender, thoroughly mixing the incoming particles until their directions are almost completely randomized. Finding a pattern in this chaos seems nearly impossible. Yet, by collecting absolutely immense datasets over many years, observatories like IceCube at the South Pole and the Pierre Auger array in Argentina are finally seeing the first faint contours of this invisible map. The initial signal is not a sharp pinpoint of light, but something much broader, a vast, gentle slope across the entire sky known as a dipole anisotropy. It is a slight but statistically significant preference for particles to arrive from one general hemisphere of the sky than the other. Think of it as a cosmic weather pattern, a prevailing wind of atomic shards blowing from a particular direction. This is not a random fluctuation. It is the first hard evidence that our position in the galaxy is not neutral, that we are sitting slightly downstream from a major source of cosmic rays, perhaps the collective output of many supernova remnants in a nearby spiral arm. The story becomes even more focused when we look at the very highest energy particles, the ultra-high-energy cosmic rays. For these rare, staggering events, magnetic deflection is less effective. Their tremendous momentum lets them punch through the magnetic fog on a straighter path. And here, the maps are starting to show tantalizing, if not yet conclusive, correlations. Some of these mighty particles appear to line up with potential extragalactic sources, like the nearby radio galaxy Centaurus A, a turbulent engine located a mere 13 million light-years away. The ultimate goal is to move from these hints and correlations to a true, detailed cartography of the cosmic ray sky, a map that would directly label the most powerful particle accelerators in our cosmic neighborhood. Every tiny detected anisotropy, every slight departure from perfect uniformity, is a monumental breakthrough. It is a single data point that, when combined with thousands of others from collaborators across the globe, begins to trace the outline of a hidden universe. This is not the work of a single team or nation. It relies on a vast international collaboration, pooling data from detectors scattered across both hemispheres to piece together a complete picture of the sky. We are slowly learning to see in the dark, and the shadows are beginning to speak. This global network of cosmic ears listens in every possible environment, from the driest deserts to the iciest plains. In the high Argentine pampas, the Pierre Auger Observatory sprawls across an area of 3,000 square kilometers, a silent landscape dotted with over 1,600 water tanks waiting for the faint blue glow of a passing particle. This is the world's largest cosmic ray observatory, a colossal net designed to catch the rarest, most energetic events, the ones that strike a single square kilometer only about once per century. Far to the south, buried deep within the pristine ice of Antarctica, lies another kind of detector. The ice cube Neutrino Observatory transforms a cubic kilometer of solid glacial ice into a colossal telescope. Its thousands of sensitive optical sensors are frozen in place, watching for the unique blue flash of a neutrino interacting with an atom, a fleeting signal from a cosmic ray's distant interaction. Meanwhile, in the deserts of Utah, the Telescope Array project scans the northern sky. Its hundreds of scintillator detectors spread across 700 square kilometers to study the ultra-high-energy spectrum and search for the origins of those mysterious fastball energy particles. Orbiting silently above them all is the Alpha Magnetic Spectrometer, mounted on the International Space Station, providing a pristine, space-based inventory of the primary cosmic rays before they ever touch our atmosphere. Each of these facilities is a masterpiece of engineering, yet none can solve the puzzle alone. The data from Auger's immense ground array must be cross-referenced with the precise particle identification from the space-based spectrometer. A high-energy event caught in Utah might be correlated with a neutrino signal from Ice Cube, offering multiple, independent witnesses to the same cosmic crime. This is the power of the global collaboration. It is a scientific symphony with instruments on every continent and in orbit, all playing different parts of the same cosmic composition. The next great leap is already taking shape. The Cherenkov Telescope Array, under construction in the clear skies of Chile and the Canary Islands, will be the most powerful gamma-ray observatory ever built. With over 100 telescopes of various sizes, it will scan the sky for the high-energy flashes that point back to cosmic ray accelerators with unprecedented sensitivity and resolution. This worldwide effort does more than just collect data. It pushes the very frontiers of technology, driving innovations in sensor design, data transmission, and computing power that ripple out into the wider world. The silent conversation between these distant stations, the careful merging of their data, is how we slowly, painstakingly, learn to read a language written in the dark. Each water tank at the Pierre Auger Observatory is a masterpiece of rugged simplicity, a self-contained listening post built to survive for decades under the harsh Argentine sun. These are not delicate laboratory instruments. They must operate flawlessly with no human intervention for weeks at a time, powered only by solar panels and communicating their precious data via a wireless mesh network. The sheer scale is staggering, keeping 1,600 of these tanks calibrated to each other, ensuring that a nanosecond timing difference between two distant units does not distort the entire picture, is a logistical and engineering nightmare. Every single sensor must tell the same story, or the cosmic message is lost in a jumble of contradictions. This challenge is magnified to an almost unimaginable degree at the Ice Cube Neutrino Observatory. Here, engineers had to lower strings of ultra-sensitive glass globes, the photomultiplier tubes, down boreholes drilled into ancient Antarctic ice, lowering them to depths of over 2 kilometers. The pressure is immense, the temperature is a constant and brutal -40 degrees Celsius, and any failure means the sensor is lost forever, frozen in time. Just keeping the holes from refreezing before the work was finished was a monumental task. For space-based instruments like the Alpha Magnetic Spectrometer, the problems are different but just as extreme. The detector had to be engineered to withstand the violent shaking of a rocket launch, the kind of force that can tear ordinary electronics apart. Once in the vacuum of space, it faces a constant bombardment from the very particles it is trying to study, a relentless radiation environment that can degrade its sensitive components over time. There is no maintenance crew in orbit, no easy way to replace a worn-out part. Every bolt, every wire, every line of code has to be perfect from the start. This relentless push against physical and technological limits is what transforms a collection of parts into a cosmic ear. The innovations born from this struggle often ripple out into our daily lives. The advanced wireless networks developed for Auger, the robust data processing algorithms created to handle the ice cube data deluge, even the radiation-hardened computer chips from space telescopes, all find secondary uses in medicine, communications, and industry. We are not just building machines to listen to the stars, we are forging the tools of our own future in the fires of cosmic inquiry. Every particle that strikes our atmosphere is a tiny sample of galactic material, a forensic clue to the universe's chemical history. Their composition is a direct window into nucleosynthesis, the cosmic alchemy that forges elements inside the fiery hearts of stars and the violent throes of their deaths. By analyzing the specific mix of elements and even different forms of the same element, known as isotopes, we can read this chemical ledger. Some elements act as a travel diary. Take lithium, beryllium, and boron. These are not cooked in large quantities inside stars. Instead, they are primarily created when heavier cosmic rays, like carbon and oxygen nuclei, slam into the slow-moving atoms of interstellar gas during their long journey. This shattering process, spallation, creates these lighter elements as shrapnel. The amount of this shrapnel we detect is a direct measure of how much stuff the original particle has traveled through. Scientists call this the path length, and it tells us the density of the galactic material between the source and Earth. It is a ruler for the void. Other isotopes serve as a cosmic clock. Consider a radioactive form of iron known as iron-60. This unstable isotope is created in supernova explosions, but it does not last forever. It decays away with a half-life of 2.6 million years. If we detect iron-60 in a cosmic ray, it means that particle was forged and accelerated in a relatively recent stellar explosion on a cosmic timescale. Its presence is a timestamp telling us the event that created it happened only a few million years ago. By combining these clues, the travel diary and the cosmic clock, we can calibrate our models of galactic chemical evolution. We can understand not just how elements are created in different types of stars and explosions, but also how efficiently they are scattered across the galaxy. This data reveals the Milky Way as a dynamic, self-enriching ecosystem. The carbon in your body, the oxygen in your lungs, were all once part of this cosmic cycle, forged in a long dead star and then carried across light years by these invisible messengers. The cosmic rays are more than just energetic bullets. They are the couriers delivering the very ingredients of worlds. The universe itself places a speed limit on its most powerful messengers. In 1966, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin calculated a fundamental cosmic barrier. They realized that the void is not empty. It is filled with the faint, cold afterglow of the Big Bang, the cosmic microwave background radiation. This omnipresent sea of photons acts like a dense fog for ultra-high energy cosmic rays. A single proton screaming through space with an energy exceeding 10 to the 20th electron volts should inevitably collide with one of these background photons. The crash is not a gentle nudge, it is a violent transformation, creating new particles, specifically pions, and draining a massive portion of the proton's original energy in the process. Over a distance of just 150 million light-years, this relentless interaction should slow these mighty particles down below the theoretical cutoff energy. This prediction, now known as the GZK cutoff, essentially defines a horizon for the highest energy universe. We should be surrounded by a cosmic quiet zone, a sphere beyond which no particle of such immense power can reach us. But our detectors have recorded a handful of events that shatter this expectation. We have seen particles that carry energies far beyond the GZK limit. They have somehow sailed right through this theoretical wall. This presents a thrilling dilemma that strikes at the heart of modern physics. Do these super GZK particles mean our understanding of particle interactions at these extreme energies is fundamentally flawed? Perhaps the laws of physics operate differently in realms of energy we can never hope to create in a laboratory like the Large Hadron Collider, or the answer could be even more startling. Maybe these particles are not from distant galaxies at all. Their sources must be relatively close by, within our local cosmic neighborhood, closer than 150 million light-years. What kind of monstrous, nearby engine could possibly generate such unbelievable power without us having clearly identified it yet? The hunt for the origin of these rule-breaking particles is more than a cosmic treasure hunt. It is a direct test of our most fundamental theories against the ultimate laboratory, the universe itself. Every one of these ultra-high energy events is a challenge, a single data point that forces us to question the very rules of reality. Our most powerful particle collider seems almost quaint when compared to the engines of deep space. The Large Hadron Collider can hurl a proton with an energy of about 10 trillion electron volts. Yet the cosmos routinely fires particles with energies 100 million times greater, forces we can scarcely comprehend, let alone manufacture. This staggering power gap points to a universe filled with natural accelerators of almost mythical scale. The secret to their operation lies not in intricate machinery, but in a beautifully simple cosmic process. Imagine a surfer patiently waiting in the ocean. They do not paddle with all their might to gain speed. Instead, they cleverly angle themselves onto an already moving wave, letting the wave's own energy carry them forward at breathtaking velocity. This is the essence of Fermi acceleration, the universe's preferred method for energizing matter. The surfer is a charged particle, and the wave is a colossal shock front blasting out from a supernova explosion. This expanding wall of energy, traveling at millions of miles per hour, creates a turbulent magnetic barrier in space. A proton caught in this chaos does not simply pass through the shockwave once. Magnetic fields on either side act like mirrors, bouncing the particle back and forth, trapping it in a frantic game of cosmic ping-pong. With each crossing of that shock front, the particle gains a little more speed, a little more energy, as if it were being kicked forward every time. It is a gradual, relentless process of theft, where the particle steals tiny increments of energy from the vast motion of the shockwave itself. After hundreds or thousands of these crossings, the particle has been boosted to a significant fraction of light speed. Only then does it finally escape its magnetic cage, flung out into the galaxy as a true cosmic ray. This elegant mechanism turns a stellar catastrophe into a steady, efficient particle gun. By studying the end products of this process, the rays that reach us, we are indirectly studying the intricate physics of astrophysical plasmas and shockwaves under conditions of energy and density that our laboratories will never achieve. These natural experiments provide a unique, irreplaceable window into high-energy physics, informing our most fundamental theories by showing us what is possible when the universe itself is the engineer. The atmosphere transforms a single cosmic bullet into a sprawling cascade of information. A single high-energy proton or ion nucleus, traveling at nearly the speed of light, finally meets resistance in the upper air. It smashes directly into the nucleus of an atmospheric gas atom, an impact of staggering violence. This collision is not a simple crash. It is a creative destruction, a burst of pure energy that condenses into a spray of new secondary particles. The most important of these are pions, unstable particles that live for only a few billionths of a second before they themselves decay. A charged pion will almost instantly break down into a muon, a heavier cousin of the electron, and an invisible neutrino. A neutral pion, however, decays into a pair of high-energy gamma rays. These gamma rays then interact with the electric fields of other atoms, creating electron-positron pairs, which in turn can produce more gamma rays. This chain reaction multiplies exponentially, a self-perpetuating avalanche of matter and energy. The entire structure expands downward through the air, a vast, pancake-shaped front of particles that can spread across several square kilometers by the time its leading edge brushes the ground. The precise architecture of this air shower is a direct translation of the original particle's identity. Scientists watch this development closely, measuring its longitudinal profile. A heavy nucleus like iron is a big, messy target. It interacts with the atmosphere almost immediately, high up, creating a shower that reaches its maximum size quickly and then fades. A lighter proton, however, is a nimble bullet. It penetrates much deeper into the atmospheric layers before it finally collides and initiates its cascade. The shower from a proton develops more gradually, peaking lower down. By analyzing the shape of this invisible firework, how it grows and then diminishes with depth, we can read the mass of the primary cosmic ray. The composition of the shower itself adds another layer of testimony. The number of muons that survive to the ground compared to the electrons provides a crucial cross-check. This entire atmospheric phenomenon, this chaotic explosion triggered by a single speck from the void, is the master key that unlocks the primary particle's identity. While cosmic rays are scattered and bent, their ghostly cousins travel in perfect, unwavering lines. These are neutrinos, the universe's most elusive messengers, born from the very same cosmic engines that create the high-energy particles we have been chasing. Inside a supernova's shockwave or the jet of an active galaxy, the accelerated protons collide with surrounding matter or light. These violent encounters do not just produce more protons. They also generate unstable particles called pions, which rapidly decay, and among the decay products are these nearly massless, neutral ghosts. Their neutrality is their superpower. Because they carry no electric charge, the galaxy's magnetic fields, which scramble cosmic ray paths so completely, have no grip on them whatsoever. A neutrino points directly back to its birthplace, a flawless cosmic arrow. For decades, detecting these high-energy astrophysical neutrinos was only a theorist's dream. Then, the ice cube neutrino observatory at the South Pole achieved the impossible. Using a cubic kilometer of pristine Antarctic ice as its detector, it captured the first confirmed high-energy neutrinos from beyond our solar system. These were not the low-energy neutrinos from our Sun, but messengers from cataclysms millions of light-years away, opening an entirely new window onto the high-energy universe. The ultimate goal now is to catch one of these ghostly particles in the act. At the same moment we see a flare of gamma rays and detect a specific type of cosmic ray shower. That single time-stamped correlation would be the smoking gun. It would be the undeniable evidence that pinpoints a specific supernova remnant or a distant blazar as a confirmed cosmic ray factory. This multi-messenger approach is our most powerful strategy. It is the scientific equivalent of triangulating a sound in a dark forest. You listen for the scattered footsteps of the cosmic rays, you look for the sudden flash of the gamma ray muzzle flash, and you wait for the silent, straight-line signal of the neutrino, which tells you exactly where the hunter is standing. The pursuit of these parallel signals, each telling a different part of the same story, is how we will finally write the definitive catalogue of the universe's most powerful particle accelerators. Our solar system floats within a vast and empty cavern. This is the local bubble, a region of space roughly 1,000 light-years across, filled with a whisper-thin, superheated gas. Its walls are not made of rock but of colder, denser interstellar clouds, the remnants of the ancient cataclysms that formed it. For the past 10 to 20 million years, a series of supernova explosions have been clearing out this space, their collective shockwaves acting like a cosmic broom, sweeping gas and dust aside and inflating this gigantic cavity. We are living inside the aftermath of stellar violence. This local environment is the first layer of context for every cosmic ray that reaches our detectors. The hot, thin gas of the local bubble offers less resistance to incoming particles than the denser galactic disk outside it. This means low-energy cosmic rays, which would be easily absorbed in a denser medium, can travel more freely here, reaching us in numbers we might not otherwise expect. Their journey, however, is not over. They must then pass through the final dynamic filter of our own solar system. The sun constantly exhales a stream of charged particles, the solar wind. This flow creates a protective magnetic shield around our planetary system called the heliosphere. For cosmic rays, entering the heliosphere is like trying to swim upstream against a powerful, magnetized river. Lower-energy galactic cosmic rays are particularly vulnerable, pushed back and scattered by this solar gale. Their intensity at Earth is not constant. It fluctuates with the sun's 11-year activity cycle. During solar maximum, when the sun is stormy and its magnetic field is tangled and fierce, the heliosphere becomes a more effective shield, and fewer cosmic rays make it through to us. During the quiet of solar minimum, the shield weakens, and the flood of particles from the galaxy increases. This is our local space weather, a rhythmic breathing that alternately conceals and reveals the cosmic background. To see the true galactic signal, we must first understand and subtract the influence of our own star and the peculiar bubble we inhabit. Scientists create sophisticated models of this entire local system, simulating how particles of different energies propagate through the local bubble and are then modulated by the heliosphere. By applying these corrections, they can digitally remove this final layer of distortion. It is the ultimate act of cosmic cleaning, wiping the local smudges from the lens to reveal the pristine message from the galaxy beyond. This lingering lithium problem challenges our deepest origin story. The Big Bang should have left a very specific chemical fingerprint across the cosmos, a precise amount of the light element lithium-7 forged in the universe's first fiery minutes. Yet when we look at the oldest stars, the pristine relics of the early galaxy, they contain only about a third of the lithium our models insist should be there. It is a quiet but persistent crack in the foundation of modern cosmology. The solution may not lie in rewriting the Big Bang itself, but in listening to the cosmic rays that have been chipping away at that primordial signal ever since. These particles are not just messengers from stellar explosions. They are active participants in a slow, galactic-scale chemistry experiment. When low-energy cosmic rays, primarily protons and alpha particles, cruise through the interstellar medium, they sometimes collide with heavier atoms like carbon or oxygen. These collisions are miniature acts of creation, shattering the heavy nuclei and producing lighter elements as fallout, including lithium and its cousin, beryllium. This process, known as cosmic ray spallation, acts as a secondary lithium factory, continuously adding new atoms to the galactic inventory over billions of years. The lithium we measure in an ancient star's atmosphere is therefore not a pure, unaltered sample from the Big Bang. It is a contaminated record, a mixture of the primordial ingredient and this later cosmic ray pollution. To isolate the original signal, we must first understand the contaminant. This is where the cosmic rays themselves become the key. By meticulously analyzing the amounts of lithium and beryllium carried within the cosmic rays that reach us, scientists can reverse engineer the efficiency of this spallation process. They can calculate how much lithium these galactic rays have been producing throughout the Milky Way's history. Subtracting this manufactured component from the total lithium observed in old stars could finally reveal the true primordial amount left by the Big Bang, potentially closing that frustrating gap between prediction and observation. It is a cosmic detective story where the clues are written in the shrapnel of atomic collisions, offering a way to peer past 13 billion years of galactic evolution and glimpse the universe's first nuclear fingerprints. The coming decade will transform our cosmic hearing from a faint whisper into a clear, resonant voice. A new generation of observatories, designed with breathtaking ambition, is poised to catch the universe's messages with a clarity we have only dreamed of. On the clear mountaintops of Chile and the Canary Islands, the Cherenkov telescope array is taking shape. This will not be a single telescope, but a coordinated fleet of over 100 individual instruments, creating the most powerful eye ever built for high-energy gamma-ray light. Its unprecedented sensitivity will allow it to see the faint, distant muzzle flashes of cosmic ray accelerators with exquisite detail, mapping them across the sky not as blurry smudges, but as sharply defined cosmic engines. On the ground, another colossal project is on the drawing board. The Giant Radio Array for Neutrino Detection, or GRAND, envisions a network of 200,000 radio antennas sprawled across mountain ranges and deserts. This vast electronic ear will listen for the faint radio whispers produced when ultra-high-energy cosmic rays and neutrinos slice through the Earth's atmosphere. Its primary goal is to catch those ghostly neutrinos from the most violent events, but it will also capture a flood of cosmic ray data, creating a census of the most energetic particles in the universe. To catch more of these incredibly rare ultra-high-energy events, plans are advancing for ground-based detectors that dwarf even the vast Pierre Auger array. We are talking about observatories that could cover 10,000 square kilometers or more, a net so immense it will finally catch a statistically significant number of these cosmic cannonballs, turning a handful of mysterious data points into a rich collection of evidence. Orbiting above it all, future space missions will continue the pristine, direct sampling work of the Alpha Magnetic Spectrometer, providing ever more precise inventories of the cosmic rays that flow through our galactic neighborhood. Together, these instruments will generate a data deluge, orders of magnitude greater than everything we have collected to date. This flood of information will allow us to create exquisitely detailed maps of the cosmic ray sky, those subtle anisotropies, revealing the hidden structure of particle winds flowing through the galaxy. We will be able to break down the composition of cosmic rays with the precision of a master chemist, identifying not just elements but specific isotopes, to read their travel diaries and cosmic clocks with newfound accuracy. The ultimate prize remains within reach, the definitive identification of the sources of the highest energy particles, those that defy the GZK cutoff. With these tools, we will not just be answering the questions we have today. We will be equipped to ask deeper, more fundamental questions about the engines of creation and the hidden laws that guide the most energetic particles in existence. The silent rain of cosmic particles becomes a tangible danger the moment we leave our planetary cradle. For an astronaut floating in the International Space Station, the risk is constant, a low-level background threat. But for crews traveling to the Moon or embarking on the long voyage to Mars, this invisible radiation transforms into one of the most significant barriers to human exploration. Galactic cosmic rays, those atomic nuclei fired from distant supernova, are relentless. They pierce through spacecraft hulls and human tissue alike, delivering tiny but powerful bursts of energy that can shred DNA and damage critical cells in the brain and central nervous system. This isn't a hypothetical future problem. Astronauts on the space station receive a higher radiation dose in a single day than the average person on Earth gets in an entire year. A mission to Mars could expose a crew to radiation levels that significantly increase their lifetime risk of developing cancer, with potential cognitive effects that remain poorly understood. The universe is speaking, and its message carries a biological cost. The challenge of shielding is far more complex than it seems. You might think a thick layer of metal would be the answer, but for the most energetic cosmic rays, it can make the problem worse. When a heavy iron nucleus traveling at nearly the speed of light slams into the dense atoms of a spacecraft's aluminum hull, the result is a catastrophic collision. The primary particle shatters, creating a secondary spray of nuclear fragments, neutrons, and other particles that flood the interior of the habitat. It is like trying to stop a bullet by throwing a bag of marbles in its path. The initial threat is replaced by a cloud of shrapnel. This has driven scientists to explore radically new solutions. One visionary concept is active magnetic shielding, which would create an artificial magnetosphere around a spacecraft, much like the one that naturally protects Earth. These powerful magnetic fields would gently deflect the charged particles away from the ship, a clean and elegant solution that avoids the secondary shower problem entirely. While the energy requirements for such a system are currently immense, it represents a potential path forward for true interplanetary travel. In parallel, researchers are investigating pharmaceutical countermeasures, drugs that could be taken by astronauts to help their bodies repair radiation damage more effectively or protect sensitive tissues from harm. These cosmic messengers, once just a subject of astronomical curiosity, have forced us to become biological innovators. Our ability to listen to the universe's story is now directly tied to our ability to protect the fragile human listeners who venture out to hear it. These silent messengers carry a profound truth about our own origins. Every atom of oxygen we breathe, every particle of iron in our blood, was once forged in the heart of a star that no longer exists. That iron nucleus detected in a cosmic ray shower began its life in the final, furious moments of a massive star's collapse, a cataclysm that scattered its enriched guts across the galaxy long before our own sun was even a glimmer in a nebula. We are not just metaphorically but literally made of stardust. Cosmic rays are the active couriers of this ongoing inheritance, continuously delivering material from those ancient stellar explosions directly to our doorstep. They are the proof that the universe is not a static backdrop, but a dynamic, participatory system. We are woven into its fabric, our very bodies composed of elements delivered across deep time by these very particles. Deciphering their scrambled messages does more than satisfy scientific curiosity. It humbles us. It reveals a cosmos of terrifying power and breathtaking beauty, operating on scales of space and time that dwarf human history. A single particle's million-year odyssey through the galactic magnetic maze makes our entire civilization feel like a fleeting whisper. Yet this realization is not a message of insignificance, but one of deep connection. We are not isolated observers on a quiet little world. We are embedded participants in a grand, unfolding story, a narrative of stellar life, death, and rebirth that we are only just learning to read. This profound link, written in the language of atomic shards, ignites a fundamental human drive. It calls to the next generation of explorers, engineers, and dreamers, challenging them to build better detectors, to ask deeper questions, and to continue translating the universe's greatest story, one particle at a time. Our journey to translate the cosmic whisper began with a single balloon flight and has expanded into a global conversation, a symphony of supercomputers and silent detectors listening to the sky. We have followed these particles from their violent births in supernova furnaces and black hole jets, across their million-year odysseys through the galactic magnetic maze, to their final, brilliant sacrifice in our own thin air. Each one is a courier carrying an encoded ledger of nucleosynthesis, a possible fingerprint of dark matter, and a direct challenge to the known limits of physics. The great puzzles persist, of course. The true origin of the most energetic particles remains shrouded. The antimatter surplus still whispers of multiple possibilities, and the profound link to the very chemistry of life is a tantalizing hypothesis. Yet with every new cascade of data, with every correlation between a neutrino and a gamma-ray flash, we learn another word, another rule of grammar in this complex cosmic language. The universe is not silent. It is in constant, booming conversation, speaking to us in a vocabulary of atomic shards and high-energy photons. Our grand and ongoing task is simply to keep listening, to keep building better ears, and to slowly, patiently become fluent in the story of everything. Let us know which cosmic mystery captivates you the most in the comments, and subscribe to join us as we continue to decode the universe, one